Okay, we're going to continue on with part number 2. So in part number 1 of the Strength of Materials series, we talked about the definition of stress, we understood how to calculate stress, and we talked about normal stress. And normal stress was a stress that had the force acting perpendicular to the surface. Now we're going to look at a second kind of stress, shear stress. Okay, so if I had a stack of papers and I wanted to separate them, I could separate them in a couple different ways. I could separate them by lifting the top layers off, or else I could separate them by sliding them apart. Shear stress is what would happen if we took a material and we broke it apart by trying to slide it in layers. Normal stress is where we take that section and we separate it by moving them directly apart. Okay, so we have a couple different types of stress, and we could think about the failure mechanisms that might exist with that material. Shear, we have a sliding separation. Normal, we have a essentially instant separation. So if we're calculating shear, it is a type of stress, so we calculate it the same way. It's a measure of force per area with units of pascals. So a shearing stress has the unit or the symbol tau, so that little small scripted t. It's a Greek character tau, and that's what we use to represent shear stress. Again, force upon area. And it's the area that would be the area that is the sliding area. Okay, so whatever area that would slide apart if it broke is the area that we would use. Now, often shear comes into play when we have a lot of different fasteners, which are often round. So we introduce the area pi r squared, and then remember we also had a secondary equation that we used, the pi d squared divided by 4. Let's do a couple of example problems and go back to working at our worksheets. Okay, so what is the difference between normal stress and shear stress? So let's remember that a normal stress condition would create a separating failure. And a shear stress would create a sliding failure. The other thing that's different about them is how is the area oriented to the applied force. So in a case of a normal failure or a normal stress, recall that we would have our force acting on the object, and the force is perpendicular or normal to essentially the area that we would consider. So we have our force acting there, and that force would be perpendicular to that surface. The sliding failure, so if we had an object and it was being subjected to a shear, so kind of a couple of sections of shear, the area, if this thing was to break, is going to be area in sort of a different direction. Okay, and so the area in this case would be parallel to the force, whereas here the area is perpendicular. Okay, how do we create shear or calculate shear stress? Well, tau, so let's say tau, which is a Greek character, is the symbol I use for shear stress, and that is the force over an area. Again, just be careful because that area is going to be different than the area that we might have considered for a normal stress. Okay, units pascals, which is also a Newton per square meter. Okay, so I have a pin 5 centimeters in diameter, and it's held in a wall and has a load of 10 kilonewtons applied downwards. What is the shear stress in this pin? Okay, so if I think about how this pin might break, if it was to break, what would happen is I would probably have a break like that. And what would happen is this entire section of pin would fall downwards, which means that I would have a sliding failure in this section. Okay, so shear is the stress that would be acting on that section. Okay, so how do we calculate shear? Well, I know that shear is going to be the force applied over the area. So what I'm going to need to do is figure out how much force and how much area. So I'm just going to draw a little diagram again, and I know that I have a 5 centimeter pin, which is equal to 0.05 meters in diameter. And if this thing was to break, I know that it would happen because of shear stress that was acting on a plane that looks like that. I could find my area. So area pi d squared by 4. You of course could also use area is equal to pi r squared and sort out your area by turning your diameter into a radius. I like the d squared approach, and if I work that out, I'm going to get an area equal to 1.963 times 10 to the negative 3 square meters. The force that I've applied would be 10 kilonewtons. It happens in the downwards direction, and 10 kilonewtons is equivalent to 10,000 newtons. So the shear in that part would be 10,000 newtons divided by 1.963 times 10 to the negative 3 square meters, and tau is going to be equal to 5094243 Newton per meter squared. May make sense to simplify it. This guy becomes a Pascal. Bouncing across here, I have two groups of 3, which means kilo and then mega. And so I could simplify that to say 5.1 megapascals. Okay. One thing that's always really important when we're talking about stress problems, no matter what kind of stress you have, no matter if you're worried about if it's normal stress, shear stress, you got to ask yourself, what would it look like if that part broke? Okay, so we took the approach in this question before and said, let's assume that this thing is going to have enough force on it to break. And if we figure out what that break is going to look like, what we want to ask ourselves is, number one, what is the break going to look like? Okay, so really, what was the new area created? Okay, that becomes your area. And what force was transmitted through that area. And that becomes your force. Divide force by area, and you've sorted out how much stress was in that part, regardless if it was shear or normal stress. One thing that you're going to need to know about is the term double shear, okay, versus single shear. So look at our case here. Maybe we have a rivet that's holding together two pieces of steel. So if we pull on those pieces of steel, then the rivet may break, and if it breaks, we would have a new area that's created and the force that created it. So that would be a shear, and we would consider that to be called single shear. It only broke the part in one place. We also could have fasteners that have multiple failure locations. So maybe we have a fastener that goes through multiple joints or sections, say in a hinge, and if it breaks in multiple places, then we're going to have multiple shear. Most common would be, we call it double shear, so it breaks in two places. So I've drawn out this section, and if we look at what happens, we have the full force going in one direction. On the outer edges of that pin, you would have half the force acting on each end, so combines to make the full force pushing back. And the full force that's pulling on this middle section, if it broke, would break in two places. And so what ends up happening is we end up with double the amount of area. So single shear, everything goes through a single plane, and our shear is force divided by area, as we've learned so far. In the case of double shear, the force goes through two planes, or we have two spots where we have a failure. So my area is doubled when I do my calculation. So my double shear is going to be force divided by 2 times the area. And we can always figure this out by thinking about how much force is transmitted and what area does it pass through. In the case of a double shear, and I look at that middle section, the area has doubled because I have 2 failure planes. All right, we're going to do an example problem back on our sheets. So a 5mm diameter pin passes through this knuckle joint. Okay, so it's going to be a joint where it can pivot. We've got an outer, 2 outer sections and an inner section. What is the average shear stress on the pin? Okay, so I'm going to draw a little diagram of the pin. Okay, so here's my pin, and I suspect if this thing was to break, it might break into 2 places. And so what I'd be left with is kind of 2 outer pieces, I guess, call it like 1, 2, and 3. 1 and 2 are going to be the outer pieces, and number 2 is going to be my inside pieces. it appears that number 2 would be pulled on by the full force, so 5 kilonewtons. And if piece number 2 broke, then I would have an area and an area. So 2 new pieces of area that were created. So in this case, if I want to figure out my stress, so my shear stress was going to be the force divided by 2 areas, because it's going to break in 2 places. My shear is going to be 5,000 newtons divided by 2 times my area. Maybe I'll figure it out over here. My area is equal to pi d squared by 4. Is going to be pi times 0.005 meters squared divided by 4. .963 times 10 to the negative 5 meters squared. So 5,000 divided by 2 times 1.963 times 10 to the negative 5 meters squared. Okay. Be careful with your calculator. If you write it out, 5,000 divided by 2 times 1.963, etc., etc. Be very careful, because the 1.963 that's on the bottom needs to be everything divided by it. Okay, so be careful with your equation like that, punching it into your calculator. Either use brackets, work out your bottom value first, and do multiple steps. But be very careful, and I would urge you to make sure that you can do that calculation. And if you can't, let's work together during a tutorial session and make sure we understand how to punch that into our calculator. So 5,000 divided by 2, and then divide it by the area. And I get a value 127,356,087.6 newtons per meter squared. So my shear, I can simplify it a little bit. So I have 3 decimal places twice, so kilo and then mega, 127.4 megapascals.